So we've gone over vapor pressure lowering, boiling point elevation, freezing point depression. The last of the four colligative properties is osmotic pressure. What's osmotic pressure? First of all, let's define what osmosis is. Osmosis refers to the passage of solvent molecules through a semi-permeable membrane. In other words, if you have, imagine you have two containers here, okay? You have pure A here, pure liquid A. Let's say A is water, okay? And here you have A plus others. Okay, so A is your solvent, and most of the time we're going to be dealing with water. Now, the boundary between these two compartments, okay, we're going to make that semi-permeable membrane. By semi-permeable, we mean it allows some molecules to pass through, but prevents others from passing through. So we're going to say that this is permeable only to A, allows only A molecules to pass. Okay? So what's observed when you have a situation like this? The tendency is for A to go from where its concentration is higher to where its concentration is lower. That's always a general tendency you'll find in nature. Things go from where it's concentrated to where it's less concentrated. So there's a tendency for A molecules or water molecules, if you're dealing with an aqueous solution, to go from the pure side to the contaminated side. Okay? So that movement of water molecules through a semi-permeable membrane is called osmosis. Okay. So what's osmotic pressure? So here, the natural tendencies from movement from high solvent concentration to low solvent concentration. What's osmotic pressure? That is the additional pressure that you have to exert on this side. Okay. So in other words, if I were to exert an extra pressure here, I can actually prevent osmosis. I can prevent water molecules from going to the left side here by exerting additional pressure on the solution. So that's called the osmotic pressure of the solution. So that's the additional pressure that you have to exert on the solution to prevent the flow of, to prevent osmosis, to prevent the flow of pure, of your solvent from the pure side. Okay? Now, that's just the minimum pressure you need, because once you've exceeded that pressure, what happens is osmosis will actually reverse. It will flow the other way. You have what's called reverse osmosis. So there's a minimum pressure you have to exert on that. There's a pressure you need to exert on that just to prevent the flow from either side. Okay? So that's called your osmotic pressure. We represent that by the capital Greek letter pi. Okay? And that turns out to be directly proportional to the molarity of solute particles in your solution. So it's MRT. R is the gas constant, okay, and T is the temperature in Kelvin. Okay, and like I said, if you exert higher pressure than that, then you have reverse osmosis. Practical application of that is in the purification of water. So if you've looked at all of these devices that they use to purify water, you might encounter, if you read up on that topic, you'll encounter the topic of reverse osmosis. Okay? So, let's see. Here's a clicker question. Suppose the left compartment in the figure shown below contains pure water, and the right compartment contains salt water. So, the one on the left is pure water, and the right compartment is salt water. Assuming the barrier allows only water molecules to pass, what's the net direction of water flow? Left to right or right to left? Is your clicker on? So let's see. Left to right, very good. From where your solvent concentration is higher to where your solvent concentration is lower. That's the direction of osmosis. Okay. Osmotic pressure of seawater is equivalent to that of an aqueous solution containing 27 grams of sodium chloride per liter. What pressure can be used to desalinate seawater by reverse osmosis at room temperature? Okay. Well, you need the pressure equal to the osmotic pressure. What would that be? It's equal to mRT. Okay? So what's our molarity? It has 27 grams sodium chloride per liter. So what's the formula for molarity? Mole solute per liter of solution, right? So how do we get mole solute? How many grams sodium chloride do we have? 27 grams. How do you change that to moles? Molar mass of sodium chloride is 58.44 grams per mole. Okay. That changes it to moles. And what's the volume of our solution? 1 liter, right? 27 grams per liter. So what's our molarity? And before I forget, what do I need to multiply this with? Multiply by 2. Okay? Because you need the total molarity of solute particles. So what is that number? Okay, 27 times 2 divided by 58.44. It's 924, so 0.924. Okay, moles per liter. Now, how many sig figs do I have here based on the given? I should only have 2 sig figs, right? So it's 0.92. I'm just keeping that extra digit there, since this is an intermediate step in the calculation. So our osmotic pressure is molarity, which is 0.924 moles per liter. What is R and what is T? Temperature is 298 Kelvin, room temperature. Okay, and so 298 Kelvin. What's the value for R? You remember that from ideal gas law? R is 0.08206 liters times atmosphere per mole per Kelvin. That's the value of R. So liter cancels out, mole cancels out, Kelvin cancels out. So you have your pressure, your osmotic pressure in atmosphere. And what would that be? Okay, so I have 0.924 times 0.08206 times 298. It's going to be 22.6. With 2 sig figs, it's going to be 23 atmospheres. Okay? So, should be about, I gave the wrong choices, huh? Should be let me see if I made a mistake in my calculation here. 27 divided by 58.44 times 2, okay, it's 0.924, times 0.08206 times 298, it's 22.6, so about 23, okay, 23 atmospheres. All right. How about this one? An intravenous solution is 5% weight by volume glucose. Calculate its osmotic pressure. This would be an example of what we would call an isotonic solution. Okay. And so what's the percent by volume of an isotonic saline solution? That means it will have, if an isotonic saline solution will have the same osmotic pressure as the glucose solution. Okay, so in other words, the first thing we need to do is calculate the osmotic pressure of this. So what would that be? MRT, right? And what is our M? How much glucose do we have? 5% weight by volume. So 5 grams of glucose. This is 5.00. Okay. 5.00 grams. How do I change that to moles? Divide by 180.2 grams per mole. And multiply by 2, by 3, or what? Just 1, because I just have 1. Your glucose doesn't dissociate. Okay, divided by, that's 5 grams in 100 mils, right? 5%. This means 5.00 grams in 100 mils. That's what percent. That's what percent weight by volume means. So that, what would I have to do here? What's my volume in liters? 0.1 liter. Okay. Now that 0.1 liter there is exact. Okay. My sig fig here is in the 5.00. There's 3 sig figs. So what's my R? 0.08206 liter times atmosphere per mole per Kelvin. And what's my temperature? 298 Kelvin. Okay. So what would that be? Well, I'm just gonna call this RT, okay? I'm just gonna leave it at RT because I'm only interested in having the same molarity, right? Same molarity will have the same osmotic pressure. So I don't even really need to calculate the RT there. So what's 5 divided by 180.2 divided by 0.1? 5 divided by 180.2 divided by 0.1 is 0.277 moles per liter. So an isotonic solution then would be one that has a molar concentration of 0.277 moles per liter, about 0.3 moles per liter. Okay, so what would be the molarity of the sodium chloride solution? It's also going to be 0.277, right? But that's the total molarity. So your sodium chloride then, the solution of sodium chloride you're going to need is 0.277 over 2 moles per liter. Why divide by 2? Because your sodium chloride is going to give you twice as many particles, right? So the molarity of sodium chloride solution would be 0.277 divided by 2. And that's going to be 0.1385 moles per liter. And what's the, how many grams would that, how would you change that to? So that's the molarity of your sodium chloride. How would you change that to percent weight by volume? You can just say 0.1385 moles of sodium chloride. How do you change that to grams? .44 grams per mole sodium chloride, right? Divide that by how many mils? 1,000 mils, okay, times 100%. Okay. Or you can just say times 100 mL per deciliter, because percent weight by volume is really grams per deciliter. Okay, so if it's just a convenient way of doing it. So what would that be? 0.1385 times 58.44 divided by 1,000 times 100. That's 0.809%. Okay. Weight by volume. Okay. So 0.8% will have the same osmotic pressure. Okay, so those are your 4 colligative properties. Let's try this one. A hypertonic solution is more concentrated and has a higher osmotic pressure. Okay. If 0.3 molar glucose is isotonic, remember we calculated it's 0.277. Which of these is hypertonic? 0.3 molar NaCl or 0.1 molar calcium chloride? Or 0.1 molar calcium chloride? Or let me add 2 choices here. Both, D, none. None of these. Ready? Ready? Okay, we're done. So what's the answer? Okay, looks like I just tricked you. What's 0.3? What's the total molarity for 0.3? I have to multiply that by 2, right? So that's higher than 0.3 molar glucose. So that's hypertonic. Okay, what about choice B? 0.1 times, what do I multiply that to get the total molarity? Calcium chloride is going to give you 1 calcium and 2 chlorine ions. So I have to multiply 0.1 by 3. That gives me 0.3. So that's isotonic. Okay. So the answer here is, looks like I misled you. A is hypertonic. Okay.